Okay, let's dive right into this explainer. We're looking at a completely unexpected hardware announcement from Google that literally left the tech world scratching its head. Normally, when a tech giant rolls out new hardware, we expect the usual: faster, smaller, more efficient, right? But what we definitely don't expect is a massive philosophical shift. One that directly challenges the undisputed king of the AI industry.
So here's the absolute game changer. Instead of just releasing a single do-it-all chip for their 8th generation AI architecture, Google quietly shipped two. Think about that. Same generation, built by the exact same silicon team, but custom designed for two completely different jobs. In an industry that's been riding the one-size-fits-all train for AI chips for, the last decade, this is a massive, massive divergence.
Which begs the ultimate question, right? Why build two chips when one will do the job? To solve this mystery, and to figure out why Google would literally split their incredibly expensive hardware development right down the middle, we've got to zoom out a bit. We need to look at the very foundation of computing itself.
All right, Section 1, Hardware Breakdown, Evolution to AI. Let's see exactly how we got from traditional computers to the explosive AI boom we're living through right now. So, for like 50 years, starting way back in the 1970s, the CPU was the undisputed engine of computing. It ran everything: your operating systems, databases, web browsers, the whole shebang. But then, right around 2012, researchers had this aha moment. They realized that GPUs, graphics processors, were actually the perfect accidental engine for AI math. By 2015, Google saw they needed something even more specialized, which birthed the TPU. And that brings us to today, facing this completely fascinating split generation. To really grasp why this shift happened, we need to look under the hood at what these chips actually do. Comparing these two side by side, it's super clear that the CPU and GPU are built for entirely different worlds. A CPU, it might have up to maybe 100 incredibly smart cores. It's juggling thousands of complex, independent tasks perfectly. But the GPU, it throws all that sophistication out the window for sheer, massive parallel volume. It groups thousands of relatively dumb cores together to just blast through a single instruction across tons of data points at the exact same time.
Now, what's genuinely wild about this is that a super simple math problem, matrix multiplication, is the exact reason the CPU hit a brick wall, and the GPU became this accidental hero. At the core of every single neural network, whether it's spitting out text or generating crazy images, is this one trivial operation. You take inputs, multiply them by weights, and add a bias. Simple, right? A CPU can do this in its sleep, but it can only do about 100 at a time. A massive AI model needs trillions of these operations in a single pass. A CPU would take literally years to do what we need done in milliseconds.
Which brings us to this absolutely staggering number: 16,000. That is the number of tiny parallel cores crammed inside a modern NVIDIA H100 GPU. Because GPUs were originally built just to calculate the color of millions of independent pixels for video games, they turned out to be structurally identical to what AI researchers were dreaming of: massive grids of numbers being multiplied and added all at once. It was a match made in heaven. But, and this is absolutely crucial, accidental is the key word here. At the end of the day, GPUs are still general-purpose parallel chips. So, to close that efficiency gap, Google stepped in and created their Custom Tensor Processing Unit, or TPU, and its secret weapon, the systolic array, is basically the ultimate purpose-built matrix multiplication engine. See, instead of fetching instructions and reading memory for every single little calculation like a GPU does, the TPU's systolic array passes data through a 2D grid like a continuous flowing wave. Numbers flow in, they're multiplied, added to a running total, and passed right to the next neighbor instantly. It spends way less time waiting on memory and way more time doing the actual math.
And guys, this isn't just some theoretical lab project. You might not even realize it, but you've been using this highly optimized TPU architecture for years. It's basically the invisible engine of the internet. It powers your Google search rankings, it drives those wildly accurate YouTube recommendations, keeping you glued to the screen, it translates languages on the fly, and it literally trains every single version of Google's flagship AI, Gemini.
Okay, so we've got the hardware evolution down. Let's move to Section 2, Training versus Inference, and start solving the mystery of why Google split their new 8th generation into two distinct chips. It all boils down to a massive realization that took the tech industry quite a while to fully accept. Just look at how these workloads diverge. Once you accept that teaching an AI model and then actually querying that AI model stress the hardware in two completely opposite directions, the split makes total sense.
Training pushes massive batches of data, meaning it's totally constrained by raw compute power. But inference, that's generating just one token at a time, back to back. So it's almost entirely constrained by how fast it can access memory. To tackle that compute-bound training phase, Google built the TPU V8P. And yes, the P stands for training performance. This absolute beast connects an unbelievable 9,600 individual chips together in a single pod. They share 2 petabytes of memory to deliver 121 exaflops of raw compute throughput. I mean, that is an almost unimaginable amount of number crunching power. It's designed specifically to just crush those massive batches of data and turn what used to be months of AI training into just weeks.
But then we have inference. When you're generating responses for users in real time, raw throughput just isn't the answer. Fast memory is. Enter the TPU V8i. The I is for inference specialist. Think about modern AI today. We aren't just doing simple Q&A anymore. We're talking about really long agentic loops where an AI is calling tools, reading the results, planning the next steps, and in those loops, every single millisecond of latency compounds. So Google designed the V8i specifically to absolutely kill latency. They packed it with 384 megabytes of on-chip SRAM. That's triple the amount from the previous generation, and it fundamentally changes the bottleneck. You see, SRAM is the absolute fastest memory a chip can access because it sits right there next to the processing cores. By putting the model's key value cache directly in this ultra-fast SRAM, instead of waiting on external memory, Google dramatically cuts down the wait time for generating every single token. And get this. Google didn't even stop at the accelerators. To top the whole thing off, both of these new TPUs run on Google's Axion ARM CPU. That's the host processor. What this means is that, for the first time ever, Google has gone fully in-house from top to bottom. By controlling both the CPU and the TPU, they're claiming an incredible 2 times better performance per watt compared to last year's architecture. Talk about a power move. All right, stepping back from the highly technical specs for a second, let's jump to Section 3, the industry showdown, and see how these diverging strategies are shaking up the entire tech landscape. We are honestly looking at a fascinating showdown right now. On one side, we've got NVIDIA's wildly successful generalist approach. I mean, for a decade, their playbook has been build one incredibly powerful GPU family, sell millions of them, and let the software developers figure out how to optimize the specific workloads. But on the other side, we have Google's aggressive push toward absolute specialization. Google is placing a massive bet that training and inference have diverged so much that a single chip just can't be optimal for both anymore. For them, specialization is the only path to true efficiency.
The writing is definitely on the wall here. Now sure, NVIDIA's stock only saw a tiny, temporary dip on the day of Google's announcement and quickly bounced back. But the architectural signal Google is sending to the market, it is loud and it is clear. They aren't just hedging their bets, they are trying to pave an entirely new road for the future of AI infrastructure. As the demands of AI continue to scale practically infinitely, pushing the very boundaries of power, cooling, and physical space in data centers all over the globe, we really have to ask ourselves, which strategy will ultimately win these hardware wars? Will the sheer flexibility of the generalist GPU maintain its iron grip? Or will these hyper-efficient, purpose-built specialist chips completely redefine how artificial intelligence is powered? Thanks so much for joining me for this explainer. I really hope this helps you decode the massive hardware shifts happening right beneath our digital